Hello everyone, I am Janil. This video is regarding my project implementation and evaluation of Quenchra answer model using end-to-end memory networks. End-to-end memory networks are a very hot topic right now. The top researchers of Facebook and Google are working on it. This is the requirement of my course, pattern recognition. So let's get started. First, I'll just let you know what we'll go through in this video. Initially, we'll go through the problem statement. Then we will see the core of the presentation, the memory networks. Then I will let you know and I'll show you what I have implemented, and then we'll see the results. So initially, problem statement. So suppose you are given a story. So this looks like a mini story, and after the story you have been asked a question. So will you be able to answer it? So let's see. If you just read the story and ask a question, where is milk, you have to first see that Antoine dropped milk here, and then you have to infer where was Antoine. So Antoine was in office. So the answer to the question where is milk is office. Humans can perform it easily. We have to infer from another statement that the milk is in office. What if computers are able to perform such tasks? This is exactly the same problem I am talking about. So let's see how we are going to solve it. Question answer model is the best model to frame any data. The knowledge can be framed very easily in question answer model. So the Facebook has released a dataset called Barbie dataset. It has 20 such tasks which have 1000 questions. This task range from single supporting fact to multi-sentence supporting fact to pathfinding problems. Few of the problems are more complex. Sometimes even humans gets confused to solve the problem. So and the dataset has two kinds of labels. There's an answer label and there's a supporting fact label. This will come into picture when we'll see the memory networks. Okay, so let's see the memory networks. Most of the machine learning algorithms today deal with low level tasks like object recognition. Object recognition doesn't require any memory. Memory networks is an attempt to add long-term memory component to make it more like an artificial intelligence. What if computers are able to remember, are able to infer? This is the same thing that is happening here. So there are two types of memory networks: strongly supervised memory network, weakly supervised memory network. What is the difference between them? Strongly supervised memory network does have labels in it. So when training the model, I'll tell the model that the answer is office and it is in this line, this two lines. In weakly supervised model, I'll just tell the model the answer is office. I won't tell it lies in which line. The model has to figure out on its own. Okay. So for the core of the memory networks, the architecture has four components: input, generalization, output, and response. The input converts the incoming data to internal feature map. Here the incoming data are sentences. Internal feature map can be taken as anything. It can be taken as pure raw text or word embeddings. Generalization updates memory. So if you see, if you're introducing a memory component here, we are able to store memory in the network. So if you see, we take input, it's on us if you want to convert it or not. If we don't convert it, then there's a raw text. If we convert it, then we use I of x. We can take I as any function. The generalization steps stores the obtained function in a memory slot. The next is the output. What output does is, output has a scoring function that takes the question and matches it with each of the memory component and calculates a score. The higher the score, the better match it is. There is something called hops. Hops means once a sentence, once a good memory score is achieved, we again take that obtained memory sentence and obtain another score. It is used when we have two supporting facts. For example, in the previous example, we know that to find office, we have to first obtain milk and then office. So these are two supporting facts. There's another question. Where is Antoine? The answer is bathroom. It is directly given in this one sentence. So it is one supporting fact. So it can be solved using one hop. The question where is milk needs two hop. Response is the output that the system gives you. It can be one word or a complete sentence. So now we'll talk about scoring functions. Scoring functions is how memory network gives us the answers. It matches different sentences and gives out a score. It takes input as a question, takes memory which we have already stored as I of x, applies a scoring function between the question and the memory, and gives out a score from which we can say that which sentence is highly correlated with the question. Scoring functions are implemented using word embeddings. Word embedding embeds a lot of words into low dimensional vector space. And the advantage of mapping those words into low dimensional vector space is we can calculate the distance between word vectors. So for example, if here you can see the question where is football and the sentence is John picked up the football. So the scoring function will take the question, find it from the memory and see what is the correlation between these two. By default, the word embeddings used are Q transpose, U transpose, UD, where Q is the question, D is the answer, and U is the matrix by which the word embeddings are obtained. This is a single layer architecture of memory networks. So as you can see, this are the these are the sentences. These are basically the stories we give as input. Here we obtain question which we want for which we want to find the answer. The sentences are converted to word embeddings, word embedding A, word embedding C. The question is converted to word embedding B. Now the word embedding B and A passes through a layer which ultimately passes through softmax. Softmax is just an activation function which calculates the probability of an event being happening. Then the word embedding C passes through a weighted sum, and after here it predicts what should be the answer. This is a multi-layer network. The advantage is we can stack such single layer networks multiple times to get a multi-layer network. It may give good accuracy or it may provide bad accuracy. It's on us how we configure those networks to obtain good results. Another thing very important in memory networks is wait time. Wait time is how you multiply your weight matrix in neural networks with the input and the output functions. So they have provided two different types of wait time: adjacent, which is similar to stack. In adjacent wait time, you pass the output weights of one layer as input weights to another layer. So it's like a hierarchical structure. Layer wise wait time means you pass the same weights to every layer. For example, here A and C being passed to every layer are same. So this is an example of layer wise wait time. Model selection. So to select a model, we have two possible options: bag of word model and positional encoding. The core difference between the bag of words model and the positional encoding is bag of word model doesn't takes into account the context. It just takes into account a single word. It doesn't know what the word is related to. On the other hand, positional encoding is a little bit more powerful. It takes into account the context. It knows what is ahead it the word and what is after the word. So I'll show you the demo of memory networks in action. First we'll see the configurations. We have used number of hops as 3. You'll get to know pretty soon what exactly does it means. Number of epochs 200. Embedding size is the word embedding size in which we want to map our word vectors. So basically what we are seeing is we are mapping x number of words to 20 dimensional vectors. Out of all the data available, we have taken 90% as original data and 10% as validation data. Model selection, we have taken position encoding with tying adjacent. So let's proceed to some demo. First I'll show you how the data looks like. So the data looks like this. This is the story given to us. After the story, we have been given a question. This is label 1 and this is label 2. Label 1 is the actual answer that we want to find. Label 2 are the supporting facts in which we can find the answer. So we can find the answer here and here. Now we need supporting facts just to train the model. In fact, we even don't need it for weakly supervised model. Now I'll show you the code. So the code is in TensorFlow. It sets the configurations here. This is the configurations we have already seen. There's another parameter called task ID. It asks, we have to tell which task we want to operate on. So initially we are operating on a very simple task 1. It's a simple single supporting task. Now I'll run the code. As you see, we are training for 100 epochs, and you can very easily see the training accuracy and validation accuracy. So for the 60th epoch, for 70th epoch, we are getting 100% training accuracy and 100% validation accuracy. So after the validation is complete, we test on the testing data. The 10% data we have just kept separate, and we obtain an accuracy of 0.99. This is pretty good. We are obtaining this accuracy because it's a very simple fact. For more complex facts, the accuracy drops down reasonably. There's a very nice visualization available that will clear a lot of things. So okay, so this is a question. The blue square is above the pink rectangle. The yellow square is right to the pink rectangle. This we are giving to the model, and we want to know, is the yellow square to the left of the blue square? It even took me a few minutes to figure it out whether it is correct or not. So let's see what a model has to say. The model says no, the yellow square is not left to the blue square. Now as you can see here, this 3 shows the number of hops. This is the value obtained from the scoring function. So you take this question and you score it with every memory stored in the network. Right now the memory stored in the network are just 2, this and this. Now you obtain a very good scoring function with the second memory. Again, you take the question, obtain memory, and again find the scoring function. You obtain another scoring function, that's even second sentence. Now you take first sentence, second sentence, and the question. This is called third hop, and you'll again get a scoring function. It's on your hands how you define number of hops. Sometimes even one hop is sufficient for one supporting facts, sometimes even more are needed. So I'll show you the results on all the 20 tasks. These are the results I have obtained on all the 20 tasks. Some of the tasks give very good performance with very less error rates. These are all error rates, but few of the tasks are horrendous. For example, task 19 is the pathfinding task, and we get 70.23% accuracy. Sorry, 70.23% error rate. It's one of the most difficult tasks. So currently the research is being going on to improve accuracy on task 19. So thank you for listening. This is a very hot topic in the artificial intelligence right now. So I encourage you to pursue this awesome research and contribute to achieve our dream of artificial intelligence. Thank you.